equation where you have more, where you just take more and more particles, then in the continuum limit this is actually well defined, and you get this transport equation that everyone wrote down, where where F here is the density, so the number of particles that there are in a small region in phase space with x and v, and it gets transported, well, the velocity change, the position change with the velocity, and the velocity change with the electric force. And then the right-hand side of the Poisson equation becomes quite a nice integral. Okay, so one thing I did here is I introduced species. So if you have particles, you need at least positively and negatively charged particles to have a neutral gas in the end. So you need to have at least 2 particles in your model. Often what people do is they actually disregard the ions. They say that the mass of an ion is so much bigger than the mass of an electron that the ion does not really move, and that we consider the ions as stationary. Okay, so this equation is collisionless, so that you don't consider any collisions between the particles. There are many situations in which you do have to consider collisions, and they will end up here instead of the 0. And in particular, if you're thinking about what happens in statistical mechanics, you think where you don't have a plasma, where you just have atoms flying around, then the atoms, they don't exert a force on that by themselves, but the only thing that is in that model is just the collisions here. So then the equation is called the Boltzmann equation. Okay, so now we get to the kind of structure that you might want to preserve. So the structure of this Poisson equation is of a Poisson system. That is also what Aaron said. So the Poisson, okay, so there are now 2 Poissons. There's the Poisson in Poisson, which is because it's a Poisson equation, and then there's the Poisson and the Poisson bracket. So I'm just going to say Poisson a lot. So the Poisson bracket in this system is given here. So these curly things, they are functionals on phase space, and the phase space here is the small f, the density function. So inside here you have functional derivatives. Aaron wrote down, it's no longer there, but go down on the board what it is. And then the Poisson bracket is given by this, where inside here you have this Poisson bracket, which is the normal Poisson bracket that you have in classical mechanics. And a consequence of this Poisson bracket is that there are many Casimirs, and these Casimirs are preserved by the exact flow. Okay, and that already gives you a bit of a problem, because normally when we think about a Poisson integrator, we think about a Poisson integrator that preserves all the Casimirs. But in this case, it's unlikely not a good thing to preserve all the Casimirs. It will probably lead to unstable solutions. So you have to make a choice here.
For the uninitiated, can you say what a Casimir is?
Sorry? Okay, so a Casimir here is, so if you have a Poisson bracket here, that means that any functional evolves according to this equation there. And a Casimir is if for whatever Hamiltonian you have, this thing is 0. So that means that it remains constant. So it does not matter the details of your Hamiltonian, but it will always be preserved. It's kind of fundamental in the physical system. Okay, so in this Poisson system, your E, the electric field, is actually a function of F, the density, because given the density of your particles, it specifies the electric field. This changes when we introduce a magnetic field. So, when you add a magnetic field, you have to do two things. The first thing is quite easy. You have to add this term here, which is the force that the magnetic field exerts on a particle. Okay, now you can, this is a more interesting system than the normal Hamiltonian systems we look at, because you can either go, if you go look at the proper momentum, the momentum that you get by starting from the Lagrangian and doing the Legendre transformation, you find that it's not m times v as it is normal, but it has this extra magnetic potential in there. So, yeah, well, this is how the magnetic potential is defined.
What about all the non-uniqueness of the magnetic potential?
So that's the thing, yeah. So this thing, it's not unique yet, but the equations that you get in the end, if you look at the equations that you get for the position and the velocity, the things that you can actually measure, you'll get the same result. It doesn't matter what gauge you use.
So you have a choice of Hamiltonians?
Yes, that's right, yeah. Okay, so this thing, if you use the P, the conjugate momentum, you get a Hamiltonian out of there. And, well, apart from that, the Hamiltonian is, yeah, you have a choice there. The other problem is that it mixes the P's and the X's, which means that you cannot use any of the splitting methods that we normally use. Normally we like the things that have a separation between potential energy and kinetic energy. The other way is don't use this potential, but just use the velocity. That also gives you a Hamiltonian formulation, but now your structure matrix J, what's normally the J here, is a non-canonical matrix. So it's this matrix here. So if normally this block would be 0. So either of these approaches means we cannot choose any of the normal methods for it. And this B hat is, we already saw it before. This is if you write this term, V cross B, if you write it as a linear map, this is the matrix of the map. Okay, so this is one thing that you need to add when you need to add magnetic effects. The other thing is that now the electric magnetic field evolves according to the Maxwell's equation. And yeah, for me the big difference is that the Maxwell electromagnetic field can sustain itself. So even if you don't have any particles in a vacuum, you can still have an electromagnetic field. Okay, so these are the equations that you get. You've seen these before also. So you have your Vlasov equation. These are the Maxwell equations. And the coupling is in the Vlasov equation. You have the electric and magnetic field for the Maxwell equation. And then in the Maxwell equations, you have the densities, the current density and the charge density, which are given by the density of your particles. Okay, the Poisson structure for this equation also has a Poisson structure, but it looks horrible. Oh well, it looks interesting. This is the same as the Vlasov Poisson equation, and these are the extra terms that you get. So I guess the Poisson structure, Katrina, that you showed is somehow a discretization of this. Hamiltonian does not look that bad. It's just what you would expect. So this Poisson bracket comes from the paper by Jerry Martin and Feinstein, and then Aaron and co-workers, they realized that you can use a splitting method to preserve this Poisson structure, at least at the continuous level. And yeah, we did I with Chinese co-workers did some further work on this. So the kind of solutions that you get. So this is the Landau damping that Aaron also talked about. The difference here is that the initial condition for me is a lot bigger than what he used. So it is in the nonlinear regime, which means that it is not actually damped. So what you see here is you see the density F against X, which is periodic, and the velocity V. And so you start with just a blob of particles around here, which is spread up, which has a spread in the velocity. It is a Gaussian spread in the velocity, and it's concentrated near this point, which is the same as this. So the difference with Aaron is that for him, the difference between the yellow region here and the purple region here was not that big. He just took a smaller perturbation, and then the perturbation will go to 0. So if you evolve in time, then it goes like B, C, D. So the one thing you see is that you get very narrow strips in velocity space. So there's quite a lot of structure in the velocity space. It's not a simple Gaussian. So there are here especially, I'm not so sure about how well everything here corresponds with reality, because what we do is we have boundary conditions here at velocity is 5 and minus 5, and there are actually quite a lot of particles, or there are actually a number of particles that hit that velocity. So the box that we have is not big enough to for me to have confidence in the bit here. Okay, and shortly about MHD, magnetohydrodynamics, which we saw in Wayne's talk, and which also in Jinchao Su with Kristo. So they also talked about magnetohydrodynamics. So what you do there is you assume more things about how the density function depends on velocity. And if you do that, you basically you more or less mirror what happens in fluid dynamics. So the equations that you get out are also the equations that are very much like fluid dynamics. So you get an Navier-Stokes equation coupled with the Maxwell equation. And the good thing about this is that this massively reduces the number of dimensions. The Vlasov equation is a partial differential equation in x and v space with 6 dimensions. And you can get rid of 1 dimension with, if you look at this gyral motion, but even 5 dimensions is a lot. Okay, the bad thing is that this assumption that you make is often not really physical. Well, it depends on the situation. But yeah, having a solution you can compute is a lot better than having a solution you can't compute. And the reason that I talked about molten metals is that this equation can also be used for molten metals. So they generate a magnetic field by themselves, and that is what creates the magnetic field in the Earth. So that's this outer core of the Earth. Okay, but let's go back to this Vlasov-Maxwell equation. So that's just the same slide as we had before. So now what I'm going to do is I'm going to talk about particle methods, which is where we take this equation and we make this answer for the density function. So basically what you get out here is you get the same equation that we started with when you assume that there are a number of particles. If you do this, normally you don't take as many particles as there are in reality, because in reality there are like 10 to the 20 particles or something like that, so you have no hope with that. So instead you think of one of these particles to be what's called a macro particle. It represents like a lot of particles that are all at the same position and at the same velocity. And this delta here, you can think of it as really a delta functional, and yeah, if you do finite elements that works quite well. If you do finite differences, then delta functional, you don't really want delta functionals in your solution, so you have to smooth it out a bit. You have to use what's called a shape function. Okay, so then these particles, which have now a position and a velocity, move along the characteristics. Basically says they move as particles. And what this particle in cell method does is it solves these equations for a lot of particles together with the Maxwell equations. And your current density is given here, and your charge density is there. So this says that if you use finite differences, you really don't want the deltas there. Yeah, even Katrina, she had a strong. So in particle in cell, how it works is you do kind of like a splitting, where you evolve the Maxwell equations and the particle equations separately. So you repeat these 4 steps over and over again, starting from the particle positions. You compute the current charge density, then you solve the Maxwell equations, then you have to compute the fields at the particle positions, and finally you do solve the equation of motion. Okay, we don't actually do that because we are not that far yet. So what we do is what's called electrostatics, which is that we just impose the magnetic field. And so we say that the magnetic field is constant, and we go back to the formulation where you don't have a magnetic field, except that you have a magnetic field acting on the particles, but you don't actually compute the magnetic field.
Why do you have B depending on X when you say B is constant?
I mean, it's constant in time here.
Oh, so there's a fixed magnetic field.
There's a fixed magnetic field, yeah. Magnetic field is imposed, yeah, that's right. So this is exactly what Anne said about the Boris method. So it's for us, for people in geometric integration, it's a splitting method where the only thing is that here use the Cayley method for computing matrix exponential here. Okay, spectrally deferred corrections. This is the bit that I had to learn. Well, this is one of the bits, but this is the thing that is the newest for me. So it comes from this 2000 paper, but the formulation that I use is the formulation from Ruprecht and Spectral.
Rookie. Rookie.
Oh, yeah. So there's an equation this is just for a general ODE. An equation we want to solve. We start with a Runge-Kutta collocation method. So we choose some collocation points and we construct the Runge-Kutta method from these collocation points. So that gives us the coefficients. And then if we have these coefficients, these are just the formula for Runge-Kutta method. Now, how spectrally deferred correction works, it's basically this formula. So what you do is it's a method for solving the stage equations iteratively. So you start with some guess for the solutions of the stage equation, and what we do is we actually just use our current solution as a guess for everything in the stage equation. And then we iterate this. So the new here is your iteration index. So you start with new equals 0, and then you compute this thing for new equals 1, 2, 3, 4, etc. There are different variants of spectral deferred correction depending on what is called the base method. So this is the easiest variant, which is where everything is explicit. So how this is derived? It's derived from a differential equation for the correction. So you can think of this, I mean, it looks very much like a time stepping method here, where you step from one stage to the next. So these C here are the collocation times. So you just step from one collocation time to the next. This is the distance between two collocation points. And this is the right-hand side of the differential equations for the correction. Now, at every iteration that you do, you gain one order in your method. So if you are looking for a method, so if your collocation method has order 5, then after 5 iterations, you actually get to the solution for small enough step size. So of course, because this is actually still an explicit method, if you have a stiff equation, then you need a very small step size for this to work. It's not a miracle. You cannot solve stiff equations with this. So what you can do with stiff equation is in this bit, which looks like an explicit Euler method, you can replace it with the implicit Euler method. So that is here, and the difference here is that the I-1 here is an I, so that it becomes an implicit method. Okay, so what we do is we don't choose either of these, but we do the same idea, but instead of Euler, we use the Boris method. So that is here. I just write this for applying the Boris method, for doing one step with the Boris method, which in the electrostatic case means that you actually have to compute the electric field. So compute the electric field, then interpolate it at the particle positions, and compute the force, get the forces from there, and then do a time step with Boris method. So the advantages is that you can reach arbitrary order depending on the collocation method that you start with. We always use a Lobato method, but that is mostly for implementation purposes, because Lobato is nice in that you have to start starting point and the end point already there. So you don't need to do anything special there. Similar to what Anne said, is that a nice thing of this method is that you don't need to implement a lot. You only need to implement all the things that you already have from your Boris method. Well, if you solve all the stage equations in one block, you have to solve a bigger system. So it's more or less like these diagonal implicit methods. Now, these are things that so time parallelism is something that what spectral deferred corrections is actually used for quite a bit. So time parallelism means you do first one big time step or one inaccurate time step to get to a certain point, and then in parallel you can do many accurate time steps. I think we came to the conclusion that this is probably not the best good argument in this particular case. If you want to do time parallelism, then there are better ways to get inaccurate solutions. You can take fewer particles, bigger grid spacing, instead of using your ODE solver. And this, I don't believe anymore that this is true. This is what we thought, but there is, one thing is you have this extra term here, which seems to destroy any good properties you have. So kind of standard test case is a two-stream instability, where you have one stream of particles going this way, one stream of particles going the other way. So this shows all the particles. This is position, velocity, and what you see here is that there are 1,000 particles, which are all on a line there. So it's actually 1,000 individual points, but you just see it as a line. So they go with velocity -1. There is a minus there. And then the red particles go the other way.
What are the charges? Are they equal or opposite?
Sorry? The charges are all equal. They're all electrons. So there is a background of ions in there that I don't show, that do not move. So what happens here is that you get an instability. That's why it's called a two-stream instability. And you'll see that the solutions you get are quite complicated. And one thing you see is that the particles in the stream that was going left and the particles in the stream that was going right, so they keep their color, so they're still red and blue, but they're completely mixed after quite a while. It's quite relaxing to look at. So one problem that if you compare it with the equations I had, the pictures I had before from the Vlasov's method, is you'll see that here you can think of averaging this to get a density, but you can already see that to get a smooth density, you need far more particles than this. You need actually quite a lot of particles to get rid of the sampling noise. Okay, so this is basically the results that says that we actually gain something. So what we use here is, let me see, so at the top M equals 3 means we use 3 collocation points. So you get the Roberto method, which is order 4. And k equals 3 means that we do 3 iterations in this Boris method. So in total, you have 3 stages, but the first stage is at the starting point, so you don't need to do anything. So there are only 2 stages where you need to compute something. But you need to do this 3 times, so the cost should be 6 times more. And what I did is I plotted it against the number of evaluations to factor out the 6. And you see that, so one thing that we notice is it's not that easy to get clean second order behavior. So this one is quite okay. So here you can see that it gets faster than the standard second order method. It levels out here because you reach the level of your spatial resolution. So one of the steps is solving the Poisson equation, which we do with the second order finite difference scheme. So you reach that error quite quickly. Okay, so what we want to do now is we want actually to put it in an electromagnetic code. This code is code that we wrote ourselves, but we don't want to do that for electromagnetics. So we are taking an existing code, Plasma Box, which is an open source code, and we are putting the spectral deferred correction Boris method in there. And then we'll see whether it really is as easy to put in as we thought it is. And so I talked about these 3 modeling approaches that all of them we've already seen today. I thought it would be good to see them all together. So the main difficulty of computing the Vlasovitz equation is that you need to compute 6-dimensional PDE. For this BIC, you need a lot of particles, and there is actually I have not seen a lot of analysis on it, but it is more or less like a Monte Carlo method, in that you put your particles in there, you evolve it, and you look at the distribution of particles. So this you get your convergence is in the order of the square root of the number of particles, which goes quite slowly. So yeah, you really need a lot of particles. And yeah, MHD, it's quite well understood, but you need your assumptions to hold. Okay, that's all for me. Thanks for your attention.
And for questions? Further questions?
So this spectrally deferred correction could in principle use any split, like different splittings or the Hamiltonian splitting, you could probably do this as well, right? Or
split
it exactly on Boris, it's just
exactly, it's just acts on an ODE. So.
But what about conservation properties?
Oh, well, you should ask. And I think you did it, but yeah, it's not good. Yes.
But you make numerical experiments, huh? Have you looked at the error conservation numerically?
Energy.
We looked at some conservation, but as far as we can see, there's nothing as conserved.
But how does it compare to I mean, Boris is not energy conserving, for instance, so. Is it getting better, or is it, but you make it more accurate, so then it
of course. I mean, it's more accurate, so in that sense it's better. But yeah, we did not look at actually whether we can see anything apart from it being more accurate. I just don't expect much.
What is the difference if you use this Boris method, this converge to the same collocation solution.
The difference is that this one converges faster in practice.
Because it's already second order.
Yeah, yeah, that's true, but that is not the complete story, because what I said is that you gain one order. You don't gain two orders with the Boris method, but it is more accurate.
Yeah, but you, in starting the iteration, you have already one H more.
Yeah, definitely, yeah. Please, please.
So this the pick codes. Are you combining the yeast schemes? Did you say?
No, because it's electrostatic. We just solved the Poisson equation.
But how accurately are you solving the Poisson equation?
It's second order final differences.
Okay,
So
doesn't it worry you that you've got solving that at second order, but
Yeah, of course. If you really want to do that, then you need to have a higher order method for the Maxwell equations or the Poisson equations as well. Yes.
Yeah, well, I think what it means you might be drawing false conclusions because you're emphasising this update, but the field you're working with isn't so accurate. This is what worries me, because all the stuff that I'm doing says you start with something where really space and time are all sort of just one coordinate system that you can work with, but you're actually discretizing space with second order and time with nth order.
Yeah, that's
okay.
I mean, that's right. Yeah. So that is definitely one of the things that we need to do is have higher order schemes for and for this with the electrostatic case, it's not that difficult to have solve the Poisson equation to higher order, but yeah, with the Maxwell equations, that will be an issue. So in that respect, we have to see whether like what Wikipedia apparently say, this particle method is the important thing to optimize, and how far that is really true, which depends, of course, very much on the situations that you're looking at.
Because we should be writing a higher order big code, essentially.
The finite element exterior calculus generalizes E scheme with any order.
Yeah,
We should do it that way, probably.
yeah, definitely, yeah.
If you are using a method of Hoffman-Gringle, then obviously you have to couple it with fast multiple.
So
that's a different kind of consistent.
No, but why not?
Well,
You have incredibly precise, very, very fast method.
Okay, if there are no further questions, we thank all the speakers of the day and we go for coffee.